Have you ever wondered how we do it? How do we take our incredibly complex, three-dimensional world and teach a computer to understand it? How do we build what's essentially a digital twin of reality? Well, it's a fascinating process that turns physical objects into digital data, and it all starts with something as simple as a point.
And it often starts with something that looks a lot like this. On the left, you've got a scanner that is meticulously, painstakingly capturing the surface of Michelangelo's David, one tiny point at a time. And on the right, wow, that's the breathtaking result, a perfect digital twin. This isn't just a photograph, not even close. It's a fully realized 3D model, and it lets us preserve our cultural heritage with an absolutely incredible level of precision.
So what exactly is a digital copy like that? It's so much more than just a flat picture. You see, a 3D model is a complete digital representation of an object, something we can actually interact with, manipulate, and explore in ways a simple image could never, ever allow.
And this is where it gets really powerful. Once you have a 3D model, you can zoom in and inspect the tiniest details. You can take precise measurements of its length, its area, even its volume. You can drop that object into a virtual world for a video game or an augmented reality app on your phone. Heck, you can even hit print and reproduce it with a 3D printer. The uses are they're everywhere, from preserving history to literally building the future.
But there's a fundamental problem here. As amazing as all this sounds, computers really struggle to see in 3D. It's not nearly as straightforward as, just snapping a 2D picture. It's a whole different ballgame.
And this slide just nails the contrast. In the 2D world, everything speaks one language, a nice, neat grid of pixels. Doesn't matter if it's from an old film camera or the latest smartphone, it's all just pixels. But in the 3D world, oh boy, it's the Wild West. There are dozens of ways to represent an object. You've got meshes, point clouds, voxels, you name it, and they all work completely differently.
And that means there's no single best way to represent something in 3D. It all comes down to what you actually want to do with it. You'd use one type of data for scanning an object and a completely different one for, say, animating it in a movie.
Okay, so let's start at the very beginning, with the most raw, the most fundamental form of 3D data. This is often the very first thing a scanner captures.
It's called a point cloud, and I want you to think of it as digital sand or maybe 3D confetti. A scanner, like a LiDAR sensor, shoots out light and measures millions of individual points on an object's surface. Each one of those points is simply a coordinate, an X, a Y, and a Z, just kind of floating in space.
And this is what a point cloud looks like on a massive scale. This isn't a drawing or a photo. It's a collection of millions of individual data points. It creates this beautiful, ghostly echo of a house, but at its core, it's just a cloud of disconnected dots.
And this digital dust approach has a huge, fatal flaw. Just look at these two shapes on the slide, both made of simple points. To our eyes, they look identical, right?
So the question is simple. Are these two shapes actually the same? What do you think? And maybe more importantly, what does a computer think when all it sees is a big list of coordinates?
And there it is. The moment we add connections, the truth just pops right out. One shape is a complete closed circle, and the other one's broken. See, a point cloud has no explicit connectivity. The computer has no idea which point is next to which. And this ambiguity, well, that's its critical weakness.
So, how do we solve this? How do we fix this ambiguity and give the computer that missing piece of the puzzle?
Well, it turns out we do it pretty literally by connecting the dots.
The process starts in the exact same place. As you see here in step 1, we begin by sampling that cloud of points from the dolphin's surface. This is our familiar but flawed point cloud.
But then, in step 2, the magic happens. The computer intelligently starts connecting these points with lines, which we call edges. These edges then form small, flat polygons, usually triangles, and that creates a kind of digital wireframe.
And finally, in step 3, you see the finished product, a continuous digital skin. Now, the computer no longer sees a vague cloud of dust. It sees a complete, connected surface. All that ambiguity is just gone.
This incredibly powerful structure is called a polygonal mesh. And its magic comes from 3 really simple ingredients. You have the vertices, which are just our original points, the edges, which are the lines connecting them, and the faces, which are the little polygons they create. It's this simple, elegant combination that completely solves the problem.
Okay, so we've built our digital skin. But why is this specific method, the polygonal mesh, so incredibly popular and effective in basically everything from movies to medicine?
This slide shows it perfectly. It's all about efficiency.
Imagine trying to approximate a smooth circle with flat-sided shapes. If you just use a triangle, the error is a massive 25%. But just double the sides to 6, and look, the error plummets to 6.5%. Double it again, and it shrinks even faster. This shows how a small increase in detail gives us this huge, massive gain in accuracy.
And here's the key takeaway, the secret sauce. For meshes, when you double the detail by, say, halving the edge length, you don't just cut the error in half, you reduce it by a factor of 4. It's a mathematical principle called quadratic convergence, and it's exactly why meshes are so fantastic at representing complex, smooth surfaces, like the statue of David, without needing an infinite amount of data. It's just incredibly efficient.
So we figured out how to create this amazing digital skin for objects, solving the whole ambiguity problem. But that leads to a whole new, mind-bending question. What happens when that skin has no inside or outside? What happens when our digital object is impossible? Well, that's a puzzle for another time.